In this lesson, we're going to explore properties of metals, nonmetals, and metalloids, and a little bit of naming. All right, we have a chart here where we have metals, nonmetals, and metalloids listed. We see here that we're going to put in whether or not the electronegativity and ionization energy is high or low, and whether the radius is large or small. So let's take a look at that. Metals tend to be much larger, and nonmetals tend to be much smaller. And because of that, because metals tend to be larger, the electronegativities and ionization energies tend to be lower. And because nonmetals are smaller, ionization energy and electronegativities tend to be higher. Metalloids have properties somewhere in between. So we're going to say that they are medium radius and they have medium electronegativities and ionization energies. Let's take a look at what metals do. Because they are large and those valence electrons are quite far away and there's low ionization energy, those metals are going to tend to lose electrons. Right? They're going to lose electrons. And when a neutral atom loses electrons, when something loses a negative particle, the resulting charge is that it's going to end up being positive. Right? This is what we call cation. Okay, when a neutral element loses electrons, what's left over is a positive particle that we call a cation. Nonmetals, you might guess, are going to do just the opposite. Because they are small, and because those valence electrons are close to the nucleus, they will tend to gain electrons. And when they gain electrons, they become negatively charged. We call those particles anions. Okay. Let's talk about the properties of metals versus nonmetals. First of all, metals tend to make good conductors of heat and electricity. They are malleable and ductile. And what this means is malleable means that they can be usually bent or hammered. They can change their shape when a force is applied. Ductile means that you can pull metals into a wire. So not to say that they're soft necessarily, but they are a little bit more pliable than nonmetals. Metals tend to be shiny, which the word that we should use, that you should recognize, is that they have luster. Nonmetals are going to have opposite properties from metals. They are poor conductors of heat and electricity. They're not malleable, they're not ductile. In fact, they are brittle. So if a blunt force is applied to a nonmetal, it will tend to shatter, whereas metals will tend to sort of change their shape if you hit them with a blunt force. Where metals are shiny, nonmetals are dull. They are not shiny at all. Metalloids are semiconductors, which means they sometimes conduct and sometimes they don't. This is really useful in making them into microchips for computers, because when they conduct and allow the current to go through, it's like a switch being turned on. And when they don't conduct electricity, electricity doesn't flow, and it's like a switch being turned off. And that is really the essence of how computers work. Interestingly enough, metalloids are lustrous like metals, but they are brittle like nonmetals. So that's what we're talking about, that they have properties of both. What they do with their electrons, they can either gain or lose electrons. It really depends. Metalloids will do whatever they need to do depending on what element is trying to bond with them. All right, so let's talk more about this ion business, right? So ions are formed when a neutral atom gains or loses an electron. A cation is a positive ion, and it is formed when an atom loses an electron. Elements that have either 1, 2, or 3 valence electrons will form cations. And the reason why this will happen, the whole point of why an atom wants to lose or gain electrons in the first place is it all comes down to wanting to have, the atom is trying to get 8 valence electrons is the goal. The goal is going to be 8 valence electrons. And so if an element has only 1, 2, or 3 valence electrons, it will lose either 1, 2, or 3 valence electrons, so that it will have 8 valence electrons that would be present in the next principal energy level down. An anion is a negative ion, and it is formed, I'm going to put a line here because an anion is formed when an atom gains electron and elements with either 5, 6, or 7 valence electrons will form anions. And that's because with 5, 6, or 7 valence electrons, that element is very close to having 8 valence electrons, so it just needs to gain enough valence electrons so that it has those 8 valence electrons to be stable. We'll come back to that idea here in just a minute. All right, so let's go back and revisit this idea of valence electrons. Going on to the next page. As we revisit the valence electrons, we've got this chart here that shows us everybody in this first column has 1 valence electron. Everybody in the second column has 2 valence electrons. We're skipping this. If you really want to know what valence electrons are present in the transition elements, you just need to go to your periodic table in your reference tables, and you can look that up. But we're going to stick with this part of the periodic table because it's very simple and straightforward, and that's what we're going to focus on for now. Okay. So valence electrons, first of all, are the electrons found in the outermost principal energy level. We also remember that they are responsible for the chemical reactivity of the atom. Right? If we see here that if we use aluminum as an example, right, we look up the valence electrons. Right here, there's 3 valence electrons that aluminum has. So notice that that means that aluminum is going to be in this column of the periodic table. And indeed, that is where we find it. And we notice that aluminum can form a +3 charge, because when it loses those 3 valence electrons, right, then that means that this valence shell is completely gone, and now it will have 8 electrons in its valence shell. Okay, so an ion that has a +2 charge means it's lost 2 electrons, and it will have it'll have a full valence shell that's in the previous periodic the previous period, which is 2 shells. But the octet rule is this. When an atom will either lose or gain electrons, so that it will end up with eight valence electrons. 8 valence electrons is a stable atom, meaning it is not reactive. If it has less than 8 valence electrons, that means it is unstable, and that means it will react. And so that is the key thing that we are going to rely on, that little tidbit of information. What we're going to do now is we're going to talk about, well, what happens to the size of an ion as an atom, as a neutral atom, loses or gains an electron and becomes more stable, right? So we are looking here at a metal atom. We know it's a metal atom because it has either 1, 2, or 3 valence electrons. This one has 1 valence electron. So whatever metal this is, I suppose we could count up the number of electrons. So this is 11 electrons. So this is a sodium atom. Okay, so it's starting out as neutral, meaning it's got 12 protons and 11 protons and 11 neutrons. But it is unstable. It is unstable because it has 1 valence electron and it wants 8 valence electrons. Okay, so to become stable, right, what does it have to do? It has to lose an electron. When it loses that electron, this entire principal energy level is now gone, right? Now that you don't even see that here. And the overall charge is a +1. If we keep track of the particles, we had 11 protons and 11 electrons here. We still have 11 protons, but now we lost an electron, so we have 10 electrons. So overall, the charge is 1 more positive than negative, so this becomes a cation. And it becomes a +1 charge because there's only 1 more proton than electrons, right? But the idea here is that just because it's neutral doesn't mean it's stable. This is a big concept that most students are not, you wouldn't think that that's the case. Neutral sounds like it's a good thing, but in this case, neutral is unstable. Now, what happens to the size of the atom when this atom loses its entire valence shell? The size of this ion is smaller than its atom. So in this case, we're going from a bigger atom to a smaller cation, right? And the reason here is that it lost an entire principal energy level. All right, well, let's take a look and see what we've got here. If we count up the electrons, looks like we've got 2, 10, 11, 12, 13, 14, 15, 16, 17. So this is 17 protons, 17 electrons. So this is chlorine. Okay, this is the chlorine atom. It is neutral. So it starts out being neutral, but it does not have, if we notice here, 1, 2, 3, 4, it's only got 7 valence electrons. So that means it is unstable. So what is it going to do to become stable? Well, it's going to gain an electron so that it now has a stable 8 valence electrons. But in this case, when it gains an electron, we say that it becomes an anion. Okay. In this case, we have a smaller atom, and it actually becomes a little bit bigger as an anion. And this is because you're squeezing another negative electron into the same principal energy level. And the natural effect of piling in or stuffing in 1 more negative electron into that level is that there's a repulsion effect, right? So the added electron goes into the existing principal energy level, and the ion expands. Okay. All right, let's go on and talk a little bit about naming elements and naming ions. what we are looking at here is just recognizing that there are elements of antiquity, just meaning that there's some elements that have been known since pre-recorded history, before recorded history, and these elements typically have either Greek or Latin names and symbols. And so we're talking about this just as a point of interest. You can see here, for example, iron has the symbol Fe because it's Latin for iron. That's what the Latin word for iron was. Gold, Au, comes from aurum. Mercury, Hg, is hydrogyrum, which means liquid silver, because it's a liquid silver element. So yeah, there's just sort of all these different names that don't seem to make sense today. For example, tungsten is W because its traditional name is wolfram, right? So just pointing those out as a point of interest. But when we name elements, when we name ions, we have to talk about this, whether it is, there's something slightly different, whether the ion is a metallic ion or whether it is a non-metallic ion. First of all, non-metallic ions are anions, and metallic ions are cations. Okay. What we will notice here is that metallic ions, the element name does not change. So for example, Na is the element sodium. So its name now, when it becomes an ion, is just the sodium ion. Right? Magnesium, it's a +2 ion. We just call it the magnesium ion, right? So the idea is that the element name is just staying the same. We typically will add ion at the end of it just to distinguish it, that we're talking about aluminum as the ion, not aluminum as the atom. But the name itself does not change. Now, a really interesting thing happens here. What we have here these are metals. They're typically transition metals. And these transition metals have more than one positive possible charge. They have more than one possible cation. We can see this when we go to look at the periodic table. We can see iron can either be a +2 or a +3. Cobalt can be a +2 or a +3. Copper can be a +1 or a +2. Manganese has +2, +3, +4, +7. So these transition metals that have more than one possible charge, you have to specify which ion you're referring to in the name. Right, so these transition metals that have more than one possible cation charge, they have to be, you're going to distinguish their name by using a Roman numeral. Okay, and so if the charge is a +1, we're going to use the Roman numeral 1. If the charge is a +2, we're going to use the Roman numeral +2, or just Roman numeral 2. +3 is the Roman numeral 3. Okay, and it goes on, so on and so forth. There's some other strange things that happen. There are +4s that can happen, and that's an IV, right, and so on and so forth using the Roman numeral methodology. Okay, so when you see Roman numeral, for example, if you see lead Roman numeral 4, you know we're talking about the lead +4 ion as opposed to the lead +2 ion. Okay, so that's an important thing to remember. Roman numerals are referring to the charge of the ion. All right, non-metal ions, when they become anions, their name does change a little bit, right? In this case, the suffix, the ending, changes to, the suffix becomes "ide." So, for example, oxygen, when it becomes an ion, we refer to it as oxide. Nitrogen, when it becomes a negative ion, becomes nitride. Hydrogen, when it's a negative ion, becomes hydride. Some more examples: sulfide from sulfur, phosphide from phosphorus, and chloride from chlorine, all when they become an anion. All right, that's going to be the end of this lesson for this part of the notes. We will see you back in the classroom.